I was trying to.
Let's do the after class. Okay, welcome. Sorry for the delay. New tech, and we weren't aware of it. So you notice, we have a better projector, so you can actually see something on here, and it works via HDMI, so we have sound. And I won't have to use my laptop speakers anymore to play videos to you. Okay, so today we are finishing up the data, or kind of like working on the data lecture. We went to a couple of the slides last time, but then time ran out. So I'll quickly repeat that, and then we will be talking about essentially the alphabet of visualization, the marks and channels. How can we actually encode data? This was last time. Okay, so kind of we distinguished between data set types and data types last time. So the data set types were things like tables, networks, fields, and geometry. And data types were things like the items in the table, the attributes in the table, links between nodes, for example, positions and grids. And then we made this distinction between structured and unstructured data. So essentially the gist of this is, if you want to visualize and analyze structured data, you first have to define or infer a structure from it. And there's many ways of doing this, for example, natural language processing, text mining, image analysis, computer vision, and so on. Structured data, in contrast, is what we're dealing with, and there we have things like tables, networks, fields, and geometries. We had this example of PhraseNet. So here is we have a large text body, and we simply the way we infer a structure here is by using these kind of patterns of X, S, Y, and then we have a structure from which we can derive a graph that we can then visualize. And then we talked about data semantics. So if I have just a vector like this Basil, 7S, and pair, we don't really know too much what it means, so we need to define the semantics, the real world meaning. And typically this is done in a table, for example, by a header. And here we have an ID, a name, age, shirt size, and favorite fruit. And now we know what this vector actually means. The data types, like the things that are in the cells, for example, here, are items, links, attributes, positions, and grids. And this is important to distinguish from the data types in programming. So the items are essentially the independent variables. The attributes are the dependent variables. Links is a relationship between two items. Position and grid are for spatial data sets. So, like we mentioned, that an item is an individual entity that is discrete, like a person, a patient, a car, a stock, a city, and that the attributes are defined on these items. So in this example here, we had the item person, and then we had the attributes name, age, shirt size, and favorite fruit. Yeah, I think we went over that sufficiently. And then we started talking about tables. In a flat table, we would have one item per row. So the flat table was one of the examples that I showed you earlier. So this one here, and each column is an attribute. And then we have, in a table, we always have a unique key. And that could either be the index, or it could be an explicit identifier. The thing is, of course, that it needs to be unique. And in a multidimensional table, we would have these keys like indexing based on multiple keys. So here we have a multidimensional table. We have keys are patients here, and then we have other keys that are genes. And now in here we have only one attribute, one attribute type, which would be in this case gene expression, but that's not so important. But every value here in every column is of the same type. It's of the same attribute type. So if you want to have multiple attributes in this multidimensional table, you would have to have multiple tables. And so you could have a stack of tables. And this was the kind of where we finished off last time. How we can visualize tables. Of course, we can visualize tables in Excel sheets. We can visualize them using bar charts. But we can do parallel coordinates, as we saw last time. Or we could do things like these matrices, where we simply color code these categories and encode numerical values by size. Okay, so any questions about tables, about items, about any of the things that we talked about last time before we start with graphs? Okay, great. So graphs, the definition of a graph is that it consists of a set of vertices, which are also called nodes, and a set of edges, which are also called links, that connect these vertices. And I use these names interchangeably, typically nodes, edges, links, anything like that. So vertices is the same as nodes, edges is the same as links. Here we have a very basic example, as you know from your homework, in a node link diagram style. So where we draw the nodes as circles and the links as edges. There's a couple of special graph classes that we should be aware of. So like in your homework, for example, you have a bipartite graph. We'll talk about this in a second. A simple graph is a graph that doesn't contain any loops and any multi-edges. So like here in this example, we would have two edges connecting those two nodes. So this would be a general graph, not a simple graph. And here on any loops on the node themselves, that would also make it a general graph and not a simple graph. And it's important, these graph classes and so on, they're important because you will see that we have a lot of visualization techniques that depend on a graph being of a special class, for example a tree. But some of them work with general graphs, some of them don't work with general graphs. So the tree is a graph with no cycles. So you could really like a tree, everybody knows a tree. When we draw it, we typically draw it top down, something like this. So like the tree essentially has a parent-child relationship. So we have one root node, and then we have childs that are again the root node of a subtree themselves. And the important thing is in a tree that you don't have any cross-links. So it always has this parent-child structure, so there is no links back or something like that. And that is a special property that a lot of visualization techniques make use of. So you could still work with something like this if you, for example, have a graph like this and you have this supplemental relationship. You could still show this as a tree, but then only supplement. In certain visualization techniques, you could simply add this link somehow. If the majority of it is a tree, then it doesn't break down, but typically you separate this in terms of data structure if you have additional edges in the tree. Directed graphs are also important. This is a graph that distinguishes between the difference between A to B, that we have a connection from A to B, but it doesn't imply that we also have a connection from B to A. So this example in the tree, we always have direction from a root to the children, but in a general graph, typically when we draw this, we wouldn't distinguish. Let's say in a social network, like Facebook, friendship is mutual, so it's always undirected. But let's say Twitter is not mutual. So in Twitter we would have a direction. So I am following this guy, and maybe this guy is also following me. But it's not implied, it doesn't have to be like that. So you can have this kind of relationship, like A connecting to B and B connecting to A. This would be like a valid directed graph. Then a hypergraph is where a single edge connects multiple vertices. So this is maybe something that you're not extremely familiar with, but instead of having an edge that just connects those two elements here or those two elements here, I could say I have an edge that connects all of those. And that's not the same as having two edges between them, but it's really saying these three nodes are in a specific relationship. It's not A to B, B to C, it's A, B, C, all of them are in one shared relationship. Hypergraphs are interesting, you find them a lot. You can think of them also as like set attributes on top of nodes. Many visualization techniques for graphs and trees and so on don't really work well for hypergraphs. So you have to think about something special typically. Then a bipartite graph, this is exactly what you have in your homework, where we have vertices that can be partitioned into two independent sets. So like in your homework you have games and teams, and these are two different node types, and there is no direct connection between the teams, and there is no direct connection between the games. So this is an important property. There are only edges between the two different types of vertices. It's not just two types of vertices, it's just that there is no connection here between two squares or two circles. And that's what makes up a bipartite graph. You could also have k-partite graphs where you have more than two classes. An articulation point, this is just like a couple of graph terms now that we've discussed the main graph types. An articulation point is a vertex which, if deleted from the graph, would break up a connected graph into multiple graphs or an unconnected graph. So in this example here, if I delete this node here, this would be one subgraph and this would be another subgraph. They wouldn't be connected anymore. And these articulation points, they're important in many cases because if we, for example, want to optimize a layout, we would be looking for articulation points and so on. So how can we visualize graphs? Of course, we have played around with node link diagrams quite a bit already, but there's also matrices or tree maps, and this is an implicit tree visualization, and this is a matrix visualization. And I'm actually going to open this one up here, because it's actually the same data set that we're using, that I used in the example, in the lecture. And as you can see for matrices, it really depends a lot on the order of the cells and the rows. So here I could simply switch between various orderings. I could order by name. And so how this works is that we have like each node in a column and each node in a row, and whenever we have a connection between the two of them, we simply fill out the edge, and in this case we can also color them. So we'll talk more about matrices, but the important thing to note about matrices is that they really depend a lot on the ordering. So if I, for example, sort by frequency, we will see this kind of pattern, so we can distinguish these clusters, and then if we color by the clusters, like by these groups that we had, we can clearly see the relationships. So there's mainly relationships within the groups, and then we have people like Valjean, the main character of Les Miserables. He clearly interacts with a lot of people. So we will talk in detail about when they're great and when they're not. Here's a tree map. I guess you guys have probably seen this. Like a tree map essentially partitions a space. For every subtree is assigned like an area. So we would have the root is in this case all of the imports. Who imports coffee? It wasn't roasted in 2000, not roasted in 2012. Well, here we would have all the European countries. Here we would have the North American countries and so on. So like the first level of partitioning here would be continent, and then we have individual countries, and the nodes are sized by their frequencies, like in this case by a node attribute, which is like the percentage of how much they export of overall, or how much they import of coffee overall. These are very efficient for seeing attributes. For example, if you want to see which files on your hard drive are taking up the most space, this is a very efficient visualization technique. I used it, for example, to clean up my drive. And we'll talk more about it in the graph and tree lecture. So, fields. Certain data is simply continuous. And fields capture this kind of continuous data, and they are attributes that are associated with cells. And the cells, they contain data from various type domains, for example, temperature, pressure, wind, velocity, or something like that. And this is, could be measured or it could be simulated. And the key thing here is that it's either sampling or sampling and interpolation. So let's say we want to capture temperature over the United States. Of course, every single point has a temperature, but we don't measure every single point. So we kind of only have measurements, discrete measurements at some various places, and these are the weather stations in the United States, or these are the official weather stations in the United States, and you can see that they're not equally dense. So they're more dense in densely populated areas, obviously less dense in loosely populated areas. So like if we were to ask ourselves what is the temperature in here, we would have to find out would have to find out about some kind of interpolation methods. Of course, a naive interpolation would be some linear interpolation between those points, but maybe you know more about the geography of the place, and then you would have a more sophisticated interpolation method. And the question here is like how, like all of the math about sampling is important here. Like if you had a signal processing class, you will have learned that you need to like sample a signal at a specific frequency to faithfully reproduce it, and this is of course important for continuous data. So the question is, like, what can you actually, how accurately can you actually predict data in spaces where you don't have an exact measurement. And you could sample, typically what you do is you sample on a grid. And there's a couple of different types of grids, so you have the uniform, rectilinear, structured, or unstructured grid. But obviously this grid here is completely unstructured, so it wouldn't make much sense to make a structured grid on top of the sphere of the Earth here, but it's rather unstructured. So this is a completely flexible grid arrangement. But sometimes you can actually do structured grids. So if you do an MRI scan, you simply scan every millimeter, like you have a value for every millimeter. If you want to do non-uniform sampling, so let's say you have an MRI scan and you make a scan of the whole body, but you kind of want to focus on the liver. And of course you could focus on, or you could scan for the whole body, and you could store the information for the whole body, but what is really interesting to you is the area around the liver. So you could do a more dense sampling around the liver. So you would have this kind of like denser grid in here, and just a coarse grid to give you some context outside. A structured grid is like a generalization of that, where you can simply have shapes like this. So we have like a mathematical structure behind it, but it's not a grid or rectilinear grid structure. And then unstructured is fully flexible. Of course, the advantages is here, like I don't have to store anything about the grid. I just need two values. What is the distance between the cells? But in this case, I really need to store every single position. So it kind of this goes from flexibility here to simplicity in terms of calculating the grid and storing the grid. And so in visualization, both or all of these types are actually very important. It depends on your data and it depends on the data sources. So we will have a lot of information in lecture 13, 16, 21, and 22. Essentially the scientific visualization lectures by Aaron. And here's just two examples. You could have, like, this is a visualization of an MRI scan, and you could, using different types of transfer functions, you could simply show just the bones, or you could show the muscles, or you could show all the skin, or you could show this partially, and so on. So this is kind of like the same data visualized in different ways using a different transfer function. And here we have what is called the flow visualization. This is a wind map, and this is actually interactive. So this is current data, and you can see very easily the wind stream across the country here. And it's a very, very simple visualization, but it's very effective in telling you what is going on here. And these kinds of flows, they are of course like an interesting problem in many science domains. For example, if you want to understand a combustion engine, a carburetor, or something like that, you would study those flows, and you would be interested in how hot is the air at a specific point, and so on, or what is the concentration of some chemical at a certain point, and so on. So these kind of questions is what flow visualization deals with. If we talk about geometry, we talk about the shape of items. So the example that is most relevant to visualization is typically the shape of, let's say, geographical features. Here you would have explicit spatial positions, things like points, lines, curves, surfaces, regions, volumes. This is like interesting for visualization, but not the core visualization. It's really more important in computer graphics or in computer-aided design. So if you design a car, geometry is of course really important for you. But if you, like for data visualization, it's more like for contextual information. So these are the basic data set type. I just wanted to put out a side note on academic trenches. Like in my research area, there are 3 different subdisciplines, which are called information visualization, that deals with abstract data. So this is really interesting if you, for example, are interested in never publishing or doing a thesis or whatever. So there's like the information visualization people, they have their own conference and they deal with abstract data. So tables, graphs. So essentially what this is about is being free to choose your own spatial layout. So I can simply define where I want to put my points. And of course I can't do that if I use, for example, a map. Then we have the visual analytics guys, which is InfoVis plus stats plus machine learning. And it's mostly about applications. And so, like my personal definition that this is a founding buzzword, and the people invented this to get more money from the Department of Defense and so on. So like, I consider this to be one. Many people don't, but well. And then there's the scientific visualization crowd that is really about spatial data. So that was called scientific visualization because it was mainly scientific data like MRI or flows and so on. And here it's not free to choose a spatial layout, and it's really much about finding the best way to depict the reality. And this is like typically very mathematical, so you kind of have to find algorithms and formulas to depict these data sets efficiently. And so if you were to write a computer vision predictor of whether a specific picture that you're showing is scientific visualization or information visualization, the easiest way would be look for the background color. So this is really Google search for InfoVis and SciVis, and you can see there's some outliers, but mostly InfoVis has a white background and SciVis has a black background.
It looks like the scientific viz likes to use the rainbow color scale
yes.
as well, which doesn't make sense.
This is also like InfoVis people make fun of them for that, and they make fun of us for other things. So no, but I guess that this is really from classical computer graphics. This is the older field. Like everything started in this area, and people worked on SGI machines, and like back then the background was simply black. And InfoVis is also very much much influenced from HCI and from user interfaces, from like developing for users. So like this is kind of comes a little bit more from the print graphics, and so this is probably the reason why traditionally there's more white background. So this is just a side note on academic trenches. Other data types are collections. So there's three types of collections that are important. Sets, lists, and clusters. Sets, like as in programming, sets are unique items and they're unordered. So if you have a set, you can quickly change for whether it's contained in the set, but you don't imply anything about the order. And sets are something that is very common in like a very common data form. You could also think of it as a categorical variable, and there's like some overlap between those, but you can also treat them independently as sets. And we'll have a lecture, half a lecture, on sets. Lists are simply ordered, like ordered items, and we have duplicates allowed. So it's not necessarily a table, but you could simply have a list of items. So here is a list based, like this would be the set visualization. It's of course also related to hyperedges, so hyperedges and sets are often quite related. Here we would have a visualization of lists, and I'll show you this one later at some point in detail. And clusters are groups of similar items. So here, the main thing is that you kind of make, the main difference to sets, for example, is that you make a statement about their similarity. And clustering is a very important method for aggregation and for essentially finding higher level structure in data. And in this scatter plot, we would have three clusters, the red, the green, and the blue cluster. So these are important collections. And now let's talk a little bit about the attribute types, so the things within the cells and what values they can take. So which classes of values and measurements are there? We could have categorical data, and categorical is also called nominal. So if you hear categorical and nominal, those are essentially equivalent. So in this case, you can compare equality between two items. So you have a class like fruit, gender, movie genres, or file types. Like fruit, we would have bananas, apples, and so on, and we could clearly say bananas, like this is a class. Apples are a class, but we can't say a banana is bigger than an apple. Or we can't say male is, or female is bigger than male, something like this. Then we could have ordered data, so ordinal data. These are still categorical. So the categorical would be kind of these shapes. And then in ordered data, we can't do something like multiplication, but we can define an ordering and we can compare for greater than or smaller than. So for example, shirt size. We can't say 2 times small is medium, that's not how it works, but we can say small is smaller than medium, for example. This is also true for ranking, so like the first, like something like the bestseller is, on the bestseller list, it has sold more copies than the second best sold book, but unless we have additional data, we can't say what the exact difference is. And then we have quantitative data, where we kind of allow arithmetic, so we can do addition, subtraction, multiplication, and so on, depending on the exact data type. Things like length, weight, count, temperature, and so on. So these are the important classes, and these are really important because they, for visualization, you would typically use a different visual encoding, and this is what the second half of this lecture will be about. What are the suitable visual encodings for these types of data sets? A little bit more details on quantitative data types. There's 2 different types. So there would be interval data and ratio data. And in interval data, you have arbitrary 0 values. So, for example, think of degrees in centigrade, Celsius, and Fahrenheit. Both have some arbitrary 0 values. So, centigrade has 0 is where water freezes, and Fahrenheit has, I think the story is that Fahrenheit actually went outdoors some winter in New England or whatever, and said, okay, it's not going to get colder than this, and this is 0. So as you can see, these zeros are very arbitrary, and therefore you can only compare intervals. You can say there's a difference of 5 degrees, but you can say it's not meaningful to say 20 degrees is 2 times as hot as 10 degrees. So this is simply like we kind of tend to do this, and grades are actually like this. So grade point averages is something that we shouldn't actually do. Yeah, so you just should be aware, if you don't have a real 0, you can only compare intervals, you can't do multiplications. In ratio, where you have a true 0, then there is nothing of the measured entity observed. So if I have a length of size 0, then there is simply nothing there. If something is like 1 meter long, I can clearly say that something that is 2 meter long is twice as long. So I can compare ratios and proportions in this case. And this was actually a very influential paper that kind of established the theory of scales and measurements by Stevens. And this was in the 40s, and he simply came up with these categories. He kind of like observed those categories and described them, and described what basic operations you can execute in them, the mathematical structure, and the permissible statistics. And there is still a lot of, like if you, for example, take a stats class, there is special types of statistics that you can apply to any of those data sets. So for example, if you work with categorical data, you can't do, you can't simply code one categorical value as a number and then calculate averages and so on. So this is important to really understand the difference between those data types, and especially between nominal, ordinal, and the numerical data types, because especially for visualization, because they make a big difference in how you design your visualization. So here's just like a list of operations that you can do. Again, just to repeat this, so for nominal data, you can check for equality or inequality. For ordinal data, you can check for equality, inequality, greater or smaller than. For interval data, you can do addition and subtraction in addition to that. And for ratio, you can do all of the mathematical operations, including proportions. A lot of data, when we talk about continuous data, is sequential. So we have a homogeneous flow from a minimum to a maximum. So for example, the number of people in a country starts at 0 and goes to like 1 billion and something in China. If you have diverging color scales, then you have 2 or multiple sequences that meet. And so these could happen if you have these, like if you have 0 degrees Celsius or Fahrenheit, you have this arbitrary 0, but you could also have more meaningful diverging scales, like for example the elevation above sea level. So you have a positive elevation above sea level, and then you have everything that is under the sea. So you have 2 sequences that meet. And so here would be what happens if we simply took an arbitrary color scale and used elevation to color code it. So who can distinguish something on this picture? There's one person that can guess what it is. If we design the color scale properly, you will quickly see that we are showing Florida. So the same data, and just like in one case, this was of course a super stupid color scale. But here we kind of like made a good decision on where to change the color, and we can clearly see what we're supposed to see here, the shape of southeastern US, Florida, and Cuba. You could also have cyclic data, and that's very common in temporal data. So we kind of think of time in cycles, so where we have a day that simply starts in the morning, ends in the evening. We have hours, we have weeks, we have months, we have years, and we have these cyclic patterns in our lives. They're very common. And then you could use cyclic structures or cyclic visualization techniques to show them. So this, I think, is how many people reported that they were sick. And guess what? The red thing here is Monday. And so here you can't really see that because you didn't match the cycle, which would be a week in this case. But here it shows you the cycle pretty well. So here we have one circle is 4 weeks. We have like matched the structure, and then we have this a circular layout, and then we can see this cyclic structure very well. And then we can also aggregate on various levels, especially for time. This is important. So here we have the usage of the database course website in a weekly and in a daily aggregate. So you can see there is different kind of fluctuations. So here we have daily, and here we clearly see weekend patterns. Like this is during the week, and then on the weekend it drops down, and it's during the week it drops down, and so on. Like this was, so that's important. And here we can see the weekly aggregate. So we kind of get rid of the noisy spikes, so you can't really see the weekend effects anymore. You can just see these major spikes in here. So depending on what you want to show, you should think about aggregation to reveal patterns on multiple levels. Okay, so just to repeat, in this table here, we have an item, which is also called an element or an independent variable. Here we have an attribute, which is also called a dimension, which is also called a dependent variable or a feature. So it's many different words, and it's not very consistent. I will try to stick to item and attribute. Then here we define the semantics. So where are the keys? Take a look again. Sorry?
A, B, and C, ID, date, and priority.
Yeah, you could do a compound key, but that's not necessarily unique. It's the index, exactly. So the keys here are the indices. And the reason for that is, of course, that you could order multiple products in one order. So in this table, it's really the index. And if you do this compound key, as you just suggested, you would still have, like here, we would still have not a unique situation in this little example here. What are the attribute types? So for, like, who can name categorical columns?
The order of priority.
The order is categorical?
No.
You sure?
Order priority. No, because you can compare the priorities to each other.
Exactly.
Date.
You can also compare the dates to each other. Like you can say this is
The
more
container, I'd say, would be that, because it's only one type of thing, right?
It's
Well,
also
I guess you could compare the sizes of the boxes too.
Use an order ID. The order ID is the only categorical variable here. Numerical variables. The margin, yeah. And we already established that the other ones are ordinal. So see, like we have order priority here. We can distinguish. We can do a comparison, which is more important, more higher priority. we can say a small box is smaller than a large box, and for the dates we can actually do quantitative comparison, and the only categorical one is the order ID. So, it's important to distinguish between the data and the conceptual model about the data. So data is really about the low-level description of the data, and we have all these operations that we can execute on them. And the conceptual model is what we think about it. It includes the semantics and it supports reasoning. So like we have the data, 1D floats, and conceptual, this could be temperature, or a 3D vector that floats, this could be space. So there's always this, like this relates strongly to semantics. But we can also, like, simply, depending on what we try to achieve, we can use a different transition from a data model to a conceptual model. So we have a data model, a conceptual model, temperature, and then we can do either like a quantitative interpretation, here continuous to 4 significant digits, or we can do an ordinal quantification, so is it hot, is it warm, or is it cold, or we could do like a classification into 2 categories, is it burned or is it not burned. So we can always do this kind of reasoning and derivation on data. Of course, reality is much more complicated than this. So typically, if you have a real data visualization project, you will not encounter one single flat table, but you will probably have compound data. So you will have a table with georeferences, or you would have a graph with many attributes, node attributes, and so on. The attributes could have hierarchies. Data types can be transformed, so you could simply aggregate them, or you could cluster them, and so on. So reality simply makes things a little bit more complicated, and this is also where it gets interesting, because for these very basic data types, we kind of already know how to handle them well, but if things get a little bit more compound, and if we get interesting constructions and hierarchies and relationships and so on, then there is still a space for visualization developers and visualization researchers. Okay, this concludes the data lecture. We will continue with visual variables. And so at this point, we could briefly talk about what is happening this week. You probably are all aware that homework 3 is due on Friday. I still put it on the slides here. This time I'm right. On Thursday I will talk, this is a little bit of a change in the schedule, I will talk about design guidelines, so like simple rules, especially based on experiences and tough these rules, like how you do like a sensible data visualization, and then I'll talk about tasks. And there's a little bit of a complicated sequence of reading. It's not too much, I guess, but it's just like section 6.3, 6.6, and so on. So take a look at this, and please do the reading. So before we continue, I would like to do another design critique. I'll hand out the sheets in a minute, but for this one, this is an interactive technique. It's actually an animation, so I wanted to play a video about it.
Hi, I'm Michael Ogawa, creator of CodeSwarm. This video is meant to be a companion to our paper, so it assumes some basic knowledge about our visualization technique. Due to the size limitation on videos, we cannot cover everything we wanted to. For the full story, please visit the CodeSwarm website to see the original videos. The story of Python begins with Guido van Rossum, working alone in the late 1980s. He is Python's creator and benevolent dictator for life. A year later, 2 developers join him, but they stay on the periphery of the swarm. One of them, Jack Jansen, created MacPython. His activity stands out because his sphere of influence periodically converges and diverges with Guido's. Another person, Fred Drake, appears and commits mostly blue document files. Indeed, he will become the lead documenter of Python. This pattern of Guido being the clear central developer with specialists on the periphery continues. year 2000, the popularity of Python takes off. We see many new developers coming in as the project activity increases dramatically. And for the rest of the video, the project stays busy. The Eclipse project is vastly different than Python. Right away, there is a flurry of activity. Many developers working on many files at nearly a constant pace. This is possible because these people were already working on the same project before Eclipse was open sourced. We also see that, even amid the chaos, the Eclipse project is made of many components. There are many developers clustering around the center, yet they each have their own set of files. In other words, there is not one large set of files being worked on by everybody, but many small sets of files being worked on by individuals. This can be attributed to Eclipse's rich client platform, which facilitates modular design. Looking at the commit histogram, we see something not apparent in the Python video: weekends and holidays. Weekends are the periodic gaps in the histogram occurring every 7 days. The holidays can be seen at the end of December throughout the video. These breaks further reinforce the idea that Eclipse is developed with corporate sponsorship. This final video was not produced by us, but was made after we open-sourced CodeSwarm. Alex Evans, co-founder of Media Molecule, created this using data from their Little Big Planet source control repository. It is an example of closed-source video game development and the software community adoption of CodeSwarm. At the beginning, there were only a handful of developers, mostly working on blue and purple source code. About a year and a half later, art resources like textures, plans, and levels, in orange, green, and yellow, respectively, start to be committed. Audio, in red, also appears, but less frequently. Notice that the resources tend to be committed in large batches, rather than a few at a time. The pace of development quickens as they close in on their October 2008 release date. We hope that CodeSwarm benefits the information visualization community as much as it has the software community. Thank you for watching.
Okay. So take a look at the visualization technique, rewatch one of the videos. The specific one isn't online, but other videos are. And look at the questions and we'll discuss them in 5 minutes.
Yeah, go ahead. I think the intended audience is visualization.
It might be of use to open source projects or...
I'm gonna go with nerds. I mean, I can see how you'd want to use this in any sort of code review process, any sort of process that needs.
So you feel it has a broader application?
Yeah. Like if I took my team and I ran this, you can see who's contributing what files and what area, and you can see who your experts are. So I think any sort of review process, any sort of process review.
That's why I say it's been more useful for management than for any one particular person.
You can see how management would use that. You can see how people are just like,
Well, but even team members could see, hey, if I know this, and I saw all my data files being done by this one guy, then I know I can go talk to that one guy instead of the guy who does all of the.
Sure. There's probably easier ways to see that, but
Yeah, to some degree, only if you know the project, if you know the particular project itself.
So that's a good transition into what questions does this visualization answer?
Who's doing things? Who is a very important thing? Who's contributing?
Yeah, I think he's but
it seems like something you might use for marketing to show the popularity of the project, like the sudden popularity of Python.
Well, but it doesn't do relative popularity. It shows you what inside Python is popular. People really wanted to work on the rendering engine, or they really wanted to work on the regex.
It doesn't actually show this versus C#.
Yeah, it doesn't say. I'm sure if you put, even Java next to it, Java would go crazy. Well, it had the color. The files or the different areas of the work are encoded by color. Yeah, because he said the music files are in red.
I don't think we got to see that.
But that could be just how you decide to use this tool set, but it sounds like they had some. You couldn't say this makes this whole, it's all contained or contained in its own universe. You can't say this universe is more popular than this other universe.
So what kind of data is represented?
It looks like development commits, pushes, and pulls. Just context, VCS. Yeah, I don't. It's probably only open source, so I'm guessing SVN. CSV. I keep getting the CVS mixed up with the pharmaceutical chain. We don't know that yet.
So I think we already answered how the types are.
Yes. Whatever type you could be, file extension, project, portion.
Question 7 is interesting. This visualization was much publicized in the open source community. That would make sense because you don't, unless it's a small enough group that you actually meet up, you don't have any idea of what, other than like handles on a message board. So to see names attached with or cluster and just coming and going.
Like, oh man, look at, we're all working together because it's
Yeah.
a big thing. So I think they probably got a sense of community.
It's also only meaningful to large groups. If I have a 4-guy team,
It's just going to be like stuck around in the middle.
it's. But if you have 200 developers, or some large, like Microsoft or Google, where they have thousands of engineers,
You could replace this with like sim characters, like what they're wearing or like how big their head is. So they can do like come through with
you can encode name and like the number of feathers in their headdress. Who's in charge?
So that sort of thing could be useful if you don't have another physical representation of the group.
Number 6, I think, is an interesting question.
Okay, so
I don't think you can read it very
what are
precisely.
the
And that's one of my
data types
problems
that we
with
see in this visualization? Which data types are visualized in this visualization? What is the data we see here?
You got categorical data in terms of like file types.
Yes, file types. Somebody else said usernames. So that's authors. And I guess file types would lead us to something more elementary. The files themselves. So we have files themselves, we have file types, we have authors. Something else?
Time.
Correct. So these are the main data types that we have here. And what is the relevant in white essentially when they're new or edited?
And then they cool off.
And then they cool off to the color that that assigns or that describes your file type. And also the people themselves seem to flash up a little bit when they're active. You can see that here this guy is actually like periodically increased. So what does this down here, what does that tell us?
Activity during that time.
Yeah, so this is this is the frequency over time. Like here, we essentially have this dynamic histogram that floats out. So, can you like read the data precisely here? No. No. So, what do you think is the purpose of this type of visualization?
Mostly trend analysis.
Trend analysis. Any other ideas?
How the processes are different between the three.
Yes, so that you can see structure. I can see which type of project this is. But I guess it's also a little bit about entertainment, right? It's simply fun to watch, and it's great for a community to see how their project evolved. So this tool is actually like you can plug in your SVN repository and it will create those videos for you.
It's a code selfie.
Yes, it's a code selfie. I like that too. So this was really popular back in 2010, 2011. Why do you think that is?
That's cool.
Yeah, so a lot of open source projects simply had a way to show what they're doing. And everybody could simply do it and create it. So this is also called organic visualization. So this is not so much about like there's like a subfield, a tiny subfield that is about more like giving people a feel or an idea of something without being too precise. Of course, you could do this better with bar charts. If you just want to be about precise data communication, but it's not the same. Like you engage people, you have some like organic feel to it.
Well, I thought it was interesting, like GitHub, if you click on graphs, has like stuff that shows a lot of the same data, but it takes like 4 graphs to probably not show quite as much.
Yes, and so actually the GitHub visualizations are not very good, especially the network visualization of like the dependencies between branches and forks and so on. So yeah. Any personal opinions about this piece that you want to share? Do you like it?
I think it's cool, but I don't see where I'd use it for anything.
Yeah. Okay, good. So this was something completely different to the other ones we had so far. That's also why I picked it, and I kind of like the music. Good. So, quick reminder about the no device policy. It's not been too much of an issue here, but just wanted to repeat this. And this is like the reason for that, because if you have like a Facebook notification blinking in the corner of your screen in red, your attention will be on Facebook and not on me. So like I probably won't win this fight, and therefore please don't use any devices in class when we don't use them for class activity. So let's talk about the visualization alphabet, marks and channels. So if you think about it, how can I visually represent two numbers, 4 and 8? You can give suggestions. How can I represent two numbers? Size, okay. What shape?
Square.
We have here square, 2. Okay, that's a different mathematical representation, but not a visual representation.
Velocity?
Velocity, yes, I'm not going to draw that. We could also do angle, or that would be essentially the pie chart way of doing things.
Well, wouldn't angle be like hue though? And you said hue wouldn't work as well, or?
No, you can actually you can see it clearly say this is steeper than this, and you can actually judge how much, but you can't say red is bigger than green.
These times from a single point?
Yes, that's position essentially. So you could think of more bizarre things like curvature and so on. So anything like that is possible. So this is kind of the alphabet that we're working with. So and I'll later show you a large list of how we can represent two numbers. So what we do here is we actually vary, like we have one thing, the marks that represent an item, and the other thing is a channel that essentially tells us, quantifies it somehow, that changes the appearance based on an attribute. So in terms of, in case of position, the X here is the mark, and the position is the channel. And the channel is also called a visual variable. So if you have ever heard of Jacques Partin, he kind of coined these terms of visual variables, and nowadays people call them marks and channels, but I also call them visual variables and marks. So the channels, so if I say visual variable, I also mean channel. I'm using those interchangeably. So which marks could we have? We could have the points, lines, or areas. And in 3D we could have a volume, but that's rarely used. We can use, we have a special type of marks for links, which are containment, connections, containments and connections. So like these are the basic, like if we have data items, these are the basic things that we can, how we can represent them. And if we have links, which is also an attribute type, then we could simply also use containment and connection here. Containment can of course be nested. So here is a Euler diagram of friendships. And so we can use this on multiple levels. And the channels are what controls the appearance. So essentially what we did here is we came up with a lot of different channels. They are typically proportional to or based on attributes. And proportionality is of course important for quantitative values or based on attributes, things like color, when we have qualitative attributes. So the key ones, and we've come up with more here, but the most important ones are position, shape, size, color, maybe tilt, and maybe volume. So, but essentially those four here are the key visual variables or the key channels. As I mentioned, this was kind of formalized by Jacques Partin, and he wrote this super influential book, Semiology of Graphics, in 1967, originally in French, but now you can actually get it in English too. It's still in print, and it's kind of the Bible for visualization researchers, because if you look at it, if you read it, you kind of discover, you are really amazed how much of the things were rediscovered later, and which he kind of forethought a while ago. And he really laid the groundwork, the theoretical principle for visual encoding. And this is the figure that he actually used. So he had position, size, gray value, texture, color, orientation, and shape. And for the different marks, he had points, lines, and areas. And you can see that he varied this a lot, and you can also see that he thought in terms of cartography a bit, but not only. And so texture, for example, is something that we don't really use a lot in visualization because it's not easy to distinguish, but we can. So when we want to use the marking channels, we can, based on how we change them, we can actually encode different data with them. So in this case, we have the mark is a line on the far left from your side. We have the mark is a line, and the channel is the length or position. And then we have one quantitative attribute, which is essentially encoded by the length here, and then one categorical attribute. So this would be A, B, or C. This would be the categories. So here, like this is what a bar chart can do. Like a mixture between categorical attributes and quantitative attributes. In a scatter plot, we would have the mark being a point, and then we have the channel being position. And here we could show two quantitative attributes. And this is great for showing relationships between those two quantitative attributes. If we want to add an additional categorical variable, we could add hue to that. So now we clearly see those two are in one class and this one is in one class, so we have a categorical variable added to that. And if we want another quantitative attribute, we could start varying its size. So like you could say, okay, I have a vocabulary of, like we came up with 15 different visual encodings. I could simply show 15 variables for every single point. Well, it's not like that. There is a limitation. So there is a certain kind of interaction between things. So like if, for example, you have a lot of points, then you would get clutter if some of them are really big and so on. You can also use redundant encoding. So here we're using length, position, and value. So length, obviously the length of the bars. Value, obviously how bright or dark this is. But we also use position. So like align bar charts use the size of objects, but they also use the position of the upper edge of bar charts. So like this is also why align bar charts are so efficient, because they actually use position and length. And position itself is the strongest visual variables, and length is the second most strongest. Here is an example from some weather channel. That was the snowfall in Boston in last year. And I just one rule of thumb is, if you create a bar chart, make it represent the data. Because here we have a bar chart, a bar that represents 5 inches of snow, which is about half the size of the 71 inches. And this is actually bizarre, because usually news agencies try to overemphasize effects, but in this case they kind of underemphasized it totally. So it would be much more intriguing chart if you really showed this little tiny 5 here, and the 71 up here. So yeah, obviously don't do things like that, but people still show them, and this is really just 2 numbers would be more efficient than that. So the rule here is use your channel proportional to the data, not a very surprising rule. So you can classify the channels into 2 types. You can say the magnitude channels and the identity channels. And you can see that they clearly map to these different types of data. So you can ask magnitude channels, you can ask how much, and their position, length, and saturation. And the identity channels is what and where, the shape, color, the hue of color, and the spatial region. Of course, you can use spatial region also for ordinal or quantitative data, but you can also use it for categories. So this is the classification that is in the book in your in the visualization design and analysis. And so you have position on a common state, a scale, position on an unaligned scale. You have length, it's essentially 1D size, tilt, angle, area or 2D size, the depth, like a 3D position, color luminance, color saturation, curvature, and the volume. And this here is ordered by effectiveness. And people have done studies on how effective those various attributes are, and this is really, it's not, every position here is not clearly super well understood, but we clearly know for these ones here that this is the correct ordering. And then for the identity channels, we have spatial region, which is the strongest one. Then we have color hue, then we have motion and shapes. And these attributes or these channels also have other properties. So in this case here, which visual variables, which channels are used?
Position, color.
Position and color, yes?
And size.
And size. Exactly. So we have color that shows us something, and we have a redundant encoding with position. And we have the size of the bubbles. In this example that you already know, which visual variables are used?
Color. Color.
Yeah, only color in this case. So there's a couple of characteristics how you can classify these channels. So we call a channel or selective if its mark is distinct, or if a mark is distinct from other marks. So can we make out the difference between two marks? So for example, for categories or for shapes, we can clearly distinguish those two of them. And we can also clearly distinguish the position of these 3 points from these 3 points. Associative, does it support grouping? So in this case we can clearly see that position is great for grouping, but here we can't really, like with shapes, it's really more difficult to do grouping. And then we can have this notion of magnitude versus identity channels. Is it quantitative? Can we quantify the difference between two marks? And so we can think of, like, we can analyze these channels based on these ones. So can we see an order? Magnitude versus identity again. Can we see a change in order? And length is how many unique marks can we make, and how many unique marks can be distinguished. So we, for example, know that we can distinguish only 10, 12 colors offline, like seeing, like not at the same time next to each other, but if you like have two colors, if you want to compare two colors, then you will kind of limit it to 10 or 12 colors in your visualization. But if you, for example, use symbols, you have a much stronger variety of marks that you could use. So position, as I already mentioned, is the strongest visual variable, since it's really suitable for all data types, but it also has some problems. So sometimes it's not available. So if you have flow data, for example, if you have spatial data, then you can't use position. And this is also what I mentioned, that this kind of divides scientific visualization from infovis. And it can also lead to cluttering. So if you have like a lot of items, a lot of marks in the same spot, then position isn't that great. And it is actually all of these attributes are yes for position, and we have a pretty rich vocabulary, so we can distinguish a lot of positions. So here we have, like, the scatter plot is the classical example for position. However, we are not so good at seeing position in 3 dimensions. So here we have, like, sure, there are some clues. We can, of course, in print or in projection, we don't have the stereo effect, but so we need to rely on other effects of depth. So, for example, like the size and the shading and so on, and occlusions. But it's not easy for us to read, like, for example, the exact value of this point. It would be pretty easy to read if we have a 2-dimensional scatter plot, but a 3-dimensional doesn't really work that well. So we can't really use position in 3D, yes?
So, getting highly theoretical, is it because it's on a 2D space, and perhaps if we had some hologram, would 3-dimensional?
No, so people have, yes, it's better if you have stereo, like in a physical space, but we still have these issues of, like, we can't simply align them to a scale easily. We can perceive them better if we have it in a hologram, or in like, there's things like a cave or virtual environments and so on, or if you have a virtual glasses and so on. But you still have problems, for example, of occlusion. So, like, it depends always on your viewpoint, because if you, like, of course, if you look at it so that it's 2-dimensional, you can clearly see where it belongs to. But as soon as you tilt and want to start the 3rd dimension, you kind of see that there's occlusion down here and so on. So I'll give many more lectures of why 3D isn't really such a good idea unless you have a very good reason of doing 3D. Okay, so this is the end of today. I'll have only a couple of slides left, so we'll actually get some time to spend on the next lecture next Thursday, and see you guys then.
Yeah, I needed the TA sometimes, so 2 o'clock, we're going to talk about